Hello everyone, I'm Linwei from Harbin Institute of Technology at Weihai in China. Today I will share the recent experiments results of our team about the slow-time MIMO technology applying in high-frequency surface-wave radar system. The high-frequency surface-wave radar, which is applied on surface-wave propagation, provide an excellent capability to detect ocean surface dynamical environment over the horizon. Nowadays, surface-wave radar system has been widely applied in many fields, such as detecting the sea surface conditions, surveilling the large exclusive economic zone, as well as military defense. However, HFSWR operators in the high-frequency band of 3 to 30 MHz. In order to obtain accurate angle estimates, the antenna arrays of radar system occupy a very large area. Obviously, the occupation of scarce coastal resources in a large area has become an important reason that limits the development of surface-wave radar system. Therefore, how to reduce the high land rental and construction cost is a hot research topic today. MIMO radar technology can use the spatial position relationship between different transmitting antennas to form a large number of virtual arrays so as to effectively extend to aperture of the array. MIMO technology applied to HFSWR can effectively reduce the occupied area of antenna array. Slow-time MIMO is also known as Doppler diversity, which can operate at the same time and frequency. The concept is proposed in 2006. Slow-time MIMO has the advantages of high bandwidth efficiency, easy implementation, and doesn't need to modify the receiver before range pulse compression, so that it is suitable for HFSWR. In order to apply slow-time MIMO to HFSWR, we have designed an experimental system and conduct related experiments. This paper will introduce the experiments and results of slow-time MIMO in high-frequency surface-wave radar system in recent days. Consider a MIMO radar system with M transmitters and N receivers. The transmitting signals are modulated by additional Doppler frequency in each pulse based on conventional pulse compression waveform, such as linear frequency modulation. The Q's transmitting pulse of the M's transmitter is given as shown in screen. UT is the pulse compression waveform, and the rest part of the formula denotes the Doppler shift of the transmitting signal. Consider a M-element uniform linear transmitting antenna array and a N-element uniform linear receiving antenna array. The transmitting straining vector and the receiving straining vector can be written as follows, where theta is the direction of departure, phi is the direction of arrival, d is the spacing between array elements, lambda is the wavelength of the operating frequency. Assume a far-field target with a Doppler frequency Fd, and the DOD and the DOA of the target is set t and phi t. The echo of the target from the nth receiving antenna elements in the Q's pulse is RNQ, shown in C green, where AM theta is the phase shift of the mth elements in transmitting antenna array, and the BN phi is the phase shift of the nth elements in receiving antenna array. After pulse comparison, we get XNQ. When the frequency of targets is less than the frequency interval between Wm, we can spread the echoes from different transmitters in Doppler domain. We set up the experimental radar system in Weihai, and the pictures show the location and the satellite image of the radar station. The MIMO radar experimental system has a uniform linear array consisting of 8 transmitting receiving antennas with 11.5 meters spacing. Because our experimental MIMO system has 8 transmitters and 8 receivers, we can obtain 64 virtual channels as shown in the diagram. The table shows the mainly parameters of the radar system. The carrier frequency is 4.7 MHz, and the power of each transmitter is about 100 watts. The chart shown is the signal processing results of one receiver of the radar system. The 8 transmitting signals are completely separated. Dividing the RD spectrum from each receiver into 8 equal parts, we can obtain the whole 64 virtual channels data. The right chart shows the radar RD spectrum from one of the virtual channels. Left chart shows the amplitude of slow time MIMO, single transmitter, and phased array at the same range cell. The amplitude of phased array mode is about 10 dB higher than that of slow time MIMO mode and single transmitter mode. Meanwhile, slow time MIMO and single transmitter have similar echo amplitude. MIMO technology can improve the accuracy of angle measurement and the ability of angle resolution by expanding the aperture of the array. Left chart shows the beforming results of one target echo when the radar system is working in slow time MIMO mode. The below line is the results of the sense that only antenna 1 transmits signal. The red line is the results of the sense that antenna 1 and antenna 8 transmit signals. The black line is the result of sense that all antennas transmit signals. The main lobe width of the sense with 2 transmit elements and 8 transmit elements are almost the same, which is about half of the sense with only 1 transmit element. Besides, the side lobe of sense with 8 transmit elements is lower than with 2 transmit elements. The ability of distinguish targets from different angles is also enhanced. Right chart shows the results of 2 targets in a same range cell and Doppler cell, which can be separated in slow time MIMO mode but can't be separated with a single transmitter. HFSWR has many clusters and interference, such as C cluster, ionosphere cluster, radio interference, and etc. The C cluster, mainly the first-order spectrum, has a low Doppler shift located near the shape target echoes. So the structure and the characteristics of C cluster in slow-time MIMO mode is similar to that in single transmitter mode. However, because of the slow-time MIMO mode has 64 independent virtual channels, the freedom degree and the amount of information that the slow-time MIMO mode can provide are square times that of the single transmitter mode, which has great significance for C cluster detection and separation. Unlike C cluster, ionosphere cluster may have a higher Doppler shift. Large-scale ionosphere cluster will repeat and overlap between Doppler subchannels, shown in screen. The ionosphere cluster overlap will cause more severely effect in slow-time MIMO mode than in others. So the separation of ionosphere cluster is important in slow-time MIMO. Contrary to ionosphere cluster, radio interference usually affect only a narrow bandwidth in Doppler domain. The chart shows the RG spectrum with a simulated radio signal adding in. The radio interference affects only one transmitter channels rather than all channels. Many virtual channels of slow-time MIMO are redundant, so deleting a part of them will not affect the detection performance seriously. Supposing a radio signal indenting from -10 degree, the beamforming result is affected by the interference, and the main lobe direction is shifted from 13.2 degrees to -15.3 degrees. After data deletion, the angle is restored to 13.2 degrees with some side lobe elevation. Above is the recent experiments of HFSWR based on slow-time MIMO. The experimental results proved the practicability of slow-time MIMO in HFSWR. The MIMO technology can improve the performance of angle estimating, and the MIMO system has more desired detection accuracy compared with the conventional system. In addition, the influence of interference and cluster on slow-time MIMO HFSWR is analyzed, and how to effectively suppress the cluster in slow-time MIMO HFSWR is the following study in the future. Thank you for your listening.